On the morning of February 5, 2016, staff at the Bangladesh Bank discovered the Panasonic dot matrix printer in their secure routing room had stopped working. A line of malicious code had entered the print queue, silencing the printer to hide the transactions passing through the bank's local servers. While technicians attempted to reboot the hardware, attackers used the compromised network to route nearly $1 billion out of the central banking system. This wealth was siphoned through the Swift messaging network, without the attackers ever reaching the network's central routing servers. Global financial security remains dependent on the vulnerability of these archaic physical endpoints. The Swift network operates on a rigid architecture governed by the message type standard established in 1977. This protocol was designed to replace the analog constraints of physical telex cables used throughout the early 1970s. The network payload uses a 5-block flat file structure. Transaction details are housed in Block 4, which consists of unyielding, fixed-width fields. Every transmission must match the mechanical memory limits of 1970s parsing logic, leaving no room for extra characters. Trillions of dollars in modern digital transactions are bound by these half-century-old parser constraints. Global banking is currently migrating to a new standard called ISO 2022, which utilizes expanding, nested XML data. This creates a structural conflict. A modern XML string carries deep compliance data, but it must intersect with the rigid boundaries of a legacy MT103 field. When this data exceeds legacy character limits, the translation layer deletes the excess to prevent the mainframe from crashing. Engineers call this failure silent data truncation. The system routes the money, but erases sender addresses and anti-money laundering metadata required for global compliance. Adding modern software interfaces to legacy code creates a bottleneck that fractures the underlying data. The forensics of the Bangladesh bank heist reveal how the Lazarus Group exploited these patched legacy interfaces. They targeted the local Swift Alliance access software running on the bank's internal endpoint, bypassing the central network's encryption. They deployed a specialized malware known as Trojan.Banswift directly into the local terminal. The malware altered database records in real time, allowing the attackers to issue transfer requests while hiding the evidence from the bank's internal checks. The code simultaneously severed the connection to the physical printer and wiped system logs to eliminate digital forensics. By targeting the bank's local software rather than the central network, the attackers used these isolated legacy endpoints as a backdoor into the global infrastructure. These vulnerabilities raise the question of why global financial institutions do not simply rewrite the codebase from scratch. The banking sector remains anchored to Enterprise COBOL running on ZOS mainframes, many of which were engineered decades ago. Replacing this core triggers the full rewrite trap. TSB Bank's 2018 migration failure cost hundreds of millions of dollars and locked nearly 2 million customers out of their accounts. The risk of systemic failure forces major institutions to spend up to 80% of their IT budgets maintaining these COBOL dependencies. This forces engineers into software archaeology, the mapping of undocumented legacy logic just to keep the infrastructure alive. Modern finance functions as a massive, aging industrial machine, one that civilization cannot afford to turn off.